Welcome to solverfy.
To prove the reflection based on Huygens principle, first of all, we should know what is actually a reflection. Reflection is the phenomena of light where we find that a ray of light which is incident on a reflecting surface, there is a change in the path of this light ray which takes place in the same medium. So here if I consider this is a reflecting surface, this incident ray changes its path in the same medium. And to say this particular phenomena as a reflection, there are certain laws that to be followed. The very important first law related to reflection is the angle of incidence, that is angle made by this incident ray with the normal, that must be equal to this angle of reflection. That is, this reflected ray makes an angle with the normal. That is the first thing. And whenever you find that such a relation is obeyed, then we can say that phenomena as a reflection. As well as there are other two laws related with reflection, that all these three, that is incident ray, normal and this reflected ray, these should be lie in a same plane. They must be lie in a same plane, and incident ray and reflected ray should lie on opposite side of this normal. So these are the three things which whenever we observe in case of light ray, then we can say that phenomena as a reflection. As this Huygens principle is related with the wavefront and formation of wavefront, again we should know what is the meaning of wavefront. So let's see what is wavefront. So in this figure you find that this is a spherical wavefront. So what is wavefront? If we consider a source of light which is in a isotropic medium, then these light rays travel from the source of light in all the direction with the same velocity. Let's say that velocity is c we have. So in time t, how much distance these rays will travel? Of course it is ct, as distance is velocity into time. So the rays which are reaching the distance ct in all this direction, and where all these points where the light reaches simultaneously, and if you find all those points where light reaches simultaneously are in phase, that means if I connect all those points where light reaches simultaneously and all those points are in phase, if I connect them all, then this particular structure, this particular surface, whatever is formed, is known as wavefront. And as per Huygens principle, he said that every point on this wavefront, if I consider suppose here A, B, C, 3 points, then every point on this wavefront acts like a secondary source of light, which is emitting light in again all the possible directions. So like this. So if I again here connect or take a locus of all these points, then again I will get a secondary wavelet like this. And if I draw a tangent to these surfaces, then I will get a secondary wavefront. So here the secondary wavefront would be like this. Now at the back side of this I am not drawing because Huygens said that this wavefront is more active in only forward direction. So from a spherical wavefront, primary spherical wavefront, I can able to get a secondary wavefront by drawing a tangent to this secondary surface. So this is Huygens principle, and now based on this Huygens principle we are going to prove the law of reflection, that is I is equal to R, that I am going to show at here. So for this again let us consider a plane, a reflecting surface x, y. So this surface I'll consider as a plane reflecting surface x, y. And if I consider here two rays P and Q, these are the two incident rays which are incident on this plane reflecting surface and is going to reflect as this R and S, then based on the wavefront theory, Huygens principle, we are going to show here that I is equal to R. As shown in this figure, PA and QC, these are the two incident rays. At the point where this first ray, P ray, get incident on this reflecting surface at point A, if I draw a normal N, then the angle made by this incident ray with the normal is known as angle of incidence. And the reflected ray AR, whatever it makes an angle with the normal, that we can say as angle of a reflection. Or in case of this QC ray, the angle made by QC with this normal N dash, that would be here I, and the angle made by this reflected ray CS with this N dash normal, that would be here angle of reflection R. Now, as we want to prove this reflection phenomena based on Huygens principle, so that means we need to take a wavefront. So as PA and this QC, these are the incident rays, and if you see in this diagram, the ray P, when reaches to point A here, at the same time the Q ray reaches at point B. This we can find by drawing a normal from A on this Q ray. So here AB is an incident wavefront we have. AB, this is what we have. This is incident wavefront that I can say, which is bound by two incident rays, that is incident wavefront, right? And here from this particular figure, I can show that this incident wavefront, it get incident on this reflecting surface obliquely. If you see, it's actually a way that it get incident. It incident obliquely on this XY surface, reflecting surface, and this incident wavefront makes an angle I, okay, which is equal to, I can say, angle BAC, and this is the incident angle, same as that of angle of incidence I. This is an angle made by this wavefront, angle made by incident wavefront AB with the surface, I will say, with the surface. Now every point on this particular AB, which is a incident wavefront, acts like a secondary source of light as per Huygens principle. So this A is going to emit the secondary waves. Now consider that the point B, which acts like a secondary source of light, it still doesn't reaches up to the surface. So if I consider T is the time required to reach from point B to C, then this BC distance, that I can able to write as CT, where C is the velocity of light in the air medium. And during this time T, the secondary waves from point A will cover a distance of, let's say, same as that of BC, that means CT, that much distance. So from A, suppose the same distance CT that is traveled by this A. Now if I take this CT distance as a radius and draw a spherical wavefront, draw a sphere around this point A, as you may see in this particular diagram, and if I draw a tangent from C point to this particular spherical wavefront CD, then this CD will form here, or I can call it as a reflected wavefront. This we call it as a reflected wavefront. As you may see that C is the first point of a reflected ray, right, of this second ray, of this Q ray. C is the first point, I can say, of this reflected ray, and D is already a part or point of this reflected ray AR. So I can say CD is the reflected wavefront, and the CD reflected wavefront, from the geometry of this diagram you see that makes an angle R, same as that of this angle of reflection R with the surface. So R is angle, I'll say here, angle DCA, and that is an angle made by the CD, which is a reflected wavefront with the surface. In triangle ABC and in triangle CDA, if I compare these two triangles, see in this figure, angle B and angle D. Angle B is equal to angle D and both of them are equal to 90 degree. Then as just we discuss the BC which is equal to CT we have, and AD that is also equal to we have CT. So both these sides BC and AD, those are same as their lengths are equal to CT. And in both those triangles AC is the common side. AC, this is what we have, common side. So as the two sides and angle, those are same of these two triangles, I can say the triangle ABC that is congruent or equal to triangle CDA. And hence I can able to write here the angle BAC is equal to angle DCA, and as angle BAC is angle I and angle DCA is angle R, same as that of angle of incidence and reflection, as you may see in this figure. Already we were discussed about that. So hence based on this Huygens principle we can prove this I is equal to R, angle of incidence is equal to angle of reflection, which is the law of reflection. Also, we find that this incident wavefront, this reflected wavefront, and this normal, all these lie in a same plane. This way, we can able to prove this law of reflection based on Huygens principle. Thank you.